Back yet again, our friend Surjeet Rajendran, formerly of Stanford, Johns Hopkins, MIT in an unpleasant way, and now at Berkeley. He's going to tell us about the dark sector.
Thank you very much. It's always a pleasure to come to Davis. Lots of fun here. So in this talk, I'm going to be talking about how one might search for ultralight hidden photons. And this is work done with my theory collaborators and also some experimentalist collaborators. Sami is at SLAC and Kent Irvin at Stanford. As the title suggests, this is going to be a talk where we're going to talk about how to find really light hidden photons. So basically, to the standard model, we add a very light photon, okay, a new vector boson, if you will. That vector boson has a tiny mass. That's basically how it's different from a normal photon, and the two of them are coupled together. And we're going to ask if that was true. If that was the case, how do we experimentally find it? And I'll discuss two proposals. The first proposal will be a way in which you produce and detect the hidden photon in the laboratory. So in that case, all we're really assuming is that the particle exists in the Lagrangian, and then you're asking about, can you produce it in the lab and try to see it in the lab. That'll be the first part of the talk. In the second part, I'm going to be talking about how to search for such really light particles if they happen to be the dark matter of the universe. Right? How do you build an experiment to find that if that's the dark matter? So here's the outline for the talk. I will give you a very, very brief overview of the theory motivations for finding ultralight these very light hidden photons. Then I'll talk about how you may build a laboratory experiment to produce and detect them. Okay, these kinds of ideas have been talked about before. It's not the first time that someone is talking about producing it and seeing it in the lab. But the key point of this talk is that when you have a massive photon, it's got three modes. It's got two transverse modes. The two transverse modes are the regular transverse modes of any vector boson that you know about, like the photon. But because this hidden photon has a mass, it's also got a longitudinal mode. Okay, and the key point of this talk is that the existence of this longitudinal mode makes searching for this a lot easier than people had previously thought. Okay, so that's basically the bottom line of the first part of the talk. After that, I'll basically review how one can search for this if it happened to be the dark matter of the universe. Okay, so some of you, if you come to my colloquium earlier, may have heard that part of the talk before, but the first part is something new. All right, so very briefly, the theory motivations for ultralight hidden photons. Okay, so here's what we do. We take the standard model Lagrangian, and to that we add a new U1, a new gauge boson. That's got this Lagrangian, very simple, standard kinetic term, and it's got a mass term. Okay, that's how it's different from the normal photon. So with just these two parts, the standard model doesn't talk at all to the new hidden photon. Just two completely decoupled sectors. And what we're going to do is add a small kinetic mixing between these two terms, right? F prime. F prime is the hidden photon, and F is the normal electromagnetic gauge spectrum. The very interesting thing about this coupling, right, is that this coupling is generated, could be generated anywhere in the ultraviolet. It's a dimension 4 term, right? So even if it's generated far in the ultraviolet, it will basically have, this kind of behavior, right? It's not suppressed with a high scale. It's a dimension 4 operator. So if in the far ultraviolet there happened to be some particle that had charges under both standard model and this new sector, you automatically get that kind of operator without the heavy scale suppressing it. So it's a very generic way for us to figure out if such particles existed in the ultra high energy. So that's why it's a good portal, if you will, to go and find these kinds of particles. Okay. Now we have no idea in terms of theory for where these masses can be, right? We don't even know if that particle really exists, right? So that's why we're trying to search for it. It's very popular for people to find these particles if their masses happen to be around the GeV scale. There are a lot of experimental programs underway to go and search for them. I'm not going to be interested in the GeV sector. I'm asking for really, really, really light particles, right? I'll typically be talking about particles whose masses are 10 to the minus 6 eV or smaller. So if you look at the Compton wavelengths, they're order about a meter or lighter. And the basic idea is that we don't know where these particles are, so we should just search for them wherever possible, right? Why not? One can ask, how easy is it to really get such tiny masses? Turns out that's not too hard, right? One can think about it sort of theoretically in two different limits. This is just a theory of a massive U1. Okay? Quantum mechanically, there's no problem having a massive U1. It's not like you really even need a Higgs mechanism, which you do need for non-abelian theories. So maybe there's just a hard mass that comes from somewhere in the ultraviolet, maybe from the string scale or whatever. We don't just know, we really have no idea. But that's a perfectly natural possibility as well, right? There's just a hard mass in the Lagrangian that's totally natural. That's fine. It's also possible that there's a Higgs sector associated with it. Okay. Normally, if you had a Higgs sector, you might think there should be other particles at the same scale. Okay. So you might think, should there be other particles also with the same mass? Okay, at that same scale. Do we have that? That's of course not necessarily true, because if the gauge coupling was very small, then the Higgs scale would be parametrically different from the scale of the gauge boson mass, right? So if you had a very small gauge coupling, then all these other sectors would be basically decoupled, and all you really have is just this tiny vector boson in the infrared, and that's basically what you want to find. So I think theoretically this is a pretty decent story. It could exist, and yeah.
So I'm trying to understand. There's so there are charged particles as well.
They are very heavy.
And they're very heavy.
Yes.
And their masses are
At
generated.
the masses of the charged particles.
Yeah.
We don't know where they come from, right? So they could be ultra heavy. They could be 10 to the whatever 15 GeV, God knows.
But they're generated by the Higgs mechanism with the Yukawa coupling.
This is not the standard model Higgs.
Right.
So this is some new Higgs in that sector.
Does it? Maybe I mean. So this is the generation of the gamma prime mass.
Yes.
And does the mass generation for the charged guy depend on how the?
Not on this. So the charged guys, as you know, will have a mass that depends on a Yukawa coupling.
Yeah.
Right, and that Yukawa coupling could be order 1.
Okay.
But the gauge coupling is fine. So the two of them are just decoupled. That's kind of the.
I mean, you don't have to have a charged particle, do you?
No.
You can just have a
Absolutely.
U1.
You can just have a U1 with a mass totally fine. That's what I guess people would call the Stuckelberg mechanism.
Okay.
Well, you could have a U1 with spontaneous breaking too, but
Sure. Oh, that's what we meant. Yes, absolutely. Great. So I think theoretically this is not crazy, right? It's a reasonable starting point, and one can ask, can we probe this? So what does this do, right? The basic point is that because I've introduced kinetic mixing, which is a reasonable expectation, this is going to modify the laws of electromagnetism, as we see, right? Because there's now an extra light degree of freedom around. Here's the key point about this whole story, right? So I've got two very light particles. I've got the massless photon, and I've got a slightly massive hidden photon, right? The two of them are mixed in this particular way through that coupling. And one can find two different bases in which one can talk about this. One is the mass basis, right? Where basically what you do is you diagonalize that term, and you end up with 2 degrees of freedom. One is a massless photon, okay, that couples to the standard electromagnetic current. And there's a massive hidden photon, which also couples to the same electromagnetic coupling, but with a very small epsilon mixing. Okay? So that's the mass basis. Then there is the interaction basis. In the interaction basis, you basically say there's an interacting photon. Okay? That's the photon that couples to the electromagnetic charge. And then there is a completely orthogonal component to it, which is a non-interacting hidden photon. Okay? But the two of them are mixed together by a mass mixing. So if you're familiar with the story of neutrino oscillations, this is very similar. In neutrino oscillations, you've got a flavor basis and a mass basis. Okay? The flavor basis would be the interaction basis. That's where the particles are interacting with the standard model Lagrangian. And then, but then in the flavor basis, the mass terms are not diagonal, so there is mixing between the two eigenstates. Okay? While in the mass basis, the mass states are the eigenstates, but when you produce them, you produce flavor. When you produce them in linear combinations of the mass eigenstates. Right? That's basically what happens in neutrino oscillations. So a very, very similar phenomenology also appears in this case. Okay.
So can I ask, this epsilon term you added by hand, right?
Yeah.
So this mixing is not a direct coupling. In some sense, if these two were to mix or whatever, they're going through loops? Or
they're going through loops. Exactly. So what you need is, you got to have a particle which is charged under both the standard model and this new model. Okay, and that particle can be very massive. And then there's a loop that mixes them together. Okay?
Okay.
But because this is a dimension 4 term, that heavy mass scale does not really appear. It's like a log kind of thing. So that's why it's fine. All right. So the central point of this whole story is that, as we will show in just 1 second, all of the effects of this new hidden photon have to vanish. Okay, all physical effects have to vanish when the mass of the hidden photon goes to 0. Okay, and by all physical effects, I mean all physical effects it can have on the standard model. And that's actually pretty easy to see in the interaction basis, because there you've got there are 2 degrees of freedom. There is the interacting photon and there's a non-interacting photon. And the only way these 2 sectors are even mixed with each other is through this mass mixing term, which is of course proportional to the actual mass. So this mass went away, the 2 sectors are just completely uncoupled. Okay? So all physical effects of this of the hidden photon have to vanish when the mass goes to 0. And the whole point of the talk is to ask to what power of the mass are these effects really suppressed. Okay?
So your kinetic mixing term also goes away?
Yeah, exactly. Because what you do is that
epsilon is not 0, only mass.
Yeah.
Oh.
But, yeah, so you essentially, that's right. So the epsilon term is not 0, right?
Okay.
Correct. So, but now in the massless limit, you've got one linear combination, which will be the regular photon plus epsilon of the new photon, and then there's a sterile component, which is the orthogonal component. But as of now, you have no idea what the photon really is. So you simply redefine
Oh, right.
and say that the photon is just that linear
You
combination.
reabsorb it into the photon.
Exactly.
Okay.
Okay.
So the interaction basis in the basis is the basis in which kinetic terms are diagonal.
Yeah, I mean, well, in the massless limit, that is a true statement. Yes.
In the massless.
No. In the massive limit, right? Well, I don't know. I mean, in the massive limit, right? What's happening is just the fact that there are just you certainly diagonalize the kinetic term, right?
But that one.
Yeah, exactly. Yeah.
That's when you generate this epsilon.
Exactly. Yeah. All right. So that's the point here: is that when the mass goes away, all these effects have to disappear. All right. Good. So that's the main point. We've now seen that all these effects have to disappear when the mass goes away, and now we're asking to what power is that going to affect us in our experimental reach for this. The second important point is what I already mentioned, which is that a massive hidden photon has 2 transverse modes and 1 longitudinal mode, right? And we will show that the longitudinal mode has very interesting phenomenological effects on this theory. People have already searched for these things. There are very good bounds on such particles. This is a plot of the coupling epsilon, okay, versus the mass here in EV. So as you can see, if in this mass range, let's say about 10 to the minus 6 EV and lower, one can already probe epsilons over 10 to the minus 7 roughly are constrained by a variety of experiments, CMB measurements, searches for new electromagnetic forces, Coulomb tests, etc., etc. And we want to ask, can we dig deeper into this parameter space? Okay, let's ask how we can do that. So the concept is very simple. Okay, we're going to have some source that produces these fields, the regular electromagnetic photon and the hidden photon, and then we're going to have a detector, a sensor that can respond to electromagnetic fields. Okay, because after all, whatever couples electromagnetism will also couple the hidden photon. So any detector of electromagnetic radiation is also sensitive to the hidden photon. But we of course don't care about the regular photon, right? We already know it exists. So we're going to put a shield and block it.
So doesn't that mean you do need the charged particles also? And
No, this is the charges. So all
Yeah.
particles that are charged on the standard model
yeah,
also couple to the hidden photon.
right. And what is the coupling constant? Is it the same as the standard model?
It is epsilon suppressed.
It's epsilon suppressed.
Yeah. Okay. So here's the, if you will, the idea. We have the source of the field, that's just a regular standard model particle, electrons or whatever. Those will produce both the regular electromagnetic fields and will also produce the hidden photon fields. Right? They're both produced. Regular electromagnetism is blocked by the shield. The hidden photon goes through and will also excite the field sensor. That's the key idea. Okay. So we can ask, what should the sensitivity look like in any such
First of
experiment?
all, the field sensor has to be excited not through the light photon itself, but by remixing with the real photon? Is that the way it works?
That is one way it works. We will argue there's another way. So the way that you described is how the transverse modes behave, while the longitudinal modes can go directly.
I see.
That's a key point. Yeah. Okay. So let's do a simple estimate for how big the signal should be. There are some source fields, E and B. Okay. And then if you think about it, I have to pay an epsilon price to produce a hidden photon. I also have to pay an epsilon price to detect the hidden photon. So naively, you might think that the values of the detection electric and magnetic fields should be epsilon squared times the electric and magnetic fields of the source. That's the naive estimation. What is missing from that naive estimate is that this effect has to go to zero when the mass vanishes, right? So there should be some suppression sitting out there. We're trying to figure out how big that suppression is. But before we calculate that suppression, we're looking for a very tiny effect, right? So it always helps when you're looking for a tiny effect to amplify it somehow. Okay, so how can we do that? With a static source, that's not that easy to do, but we can use resonators, right? A typical thing you might do is instead of creating a static source of the field, let's say you produce a wave of the field. This could be because, let's say, very naively, you're kind of moving some charges back and forth, so that produces some electromagnetic wave. And if you have a resonator sitting in here for your field sensor, which is tuned to that exact same frequency, then you can resonantly excite that detector. Okay? That will gain you some resonant amplification of what you're trying to do. But once again, there's the same feature. Every time you're shaking this thing and producing your electromagnetic wave, you'll produce the electromagnetic wave and the hidden photon. And the shield is supposed to block the electromagnetic wave, while the hidden photon is going to go through and excite that resonator in exactly the same way. Okay. So the answer now, if you want to do this in a very real experiment, you would use some resonance. So your final answer gets boosted by some Q factor. But once again, we need to couple. We got to figure out how the thing vanishes as the hidden photon mass goes to zero. Let's talk about that. Okay. All right. Good. So let's first discuss the case of the transverse modes. Okay. Here, this is what is happening. Let's think about it in the interaction basis, right? So when you shake your electrons, you're going to produce the interacting photon. So that's what's coupled to electrons, and that's a linear combination of both the two mass eigenstates. They're both coupled to each other, right? Now the shield is supposed to block this photon, okay? But the shield also couples to the same linear combination, right? So you might think that whatever is produced here gets completely blocked by that shield, even though it contains a little bit of the hidden photon. That, of course, is not true, right? The reason why that's not completely true is because of the fact that there is a mass mixing, right? Because there's a mass mixing, even though you produce this interacting photon, that linear combination, as that photon propagates out, right? Because of the mass mixing, it will develop a small amount of the hidden photon in it. Much like neutrino oscillations. You will oscillate a little bit in the hidden photon, right? So there will be some hidden photon component produced over here that is proportional to this mass square that goes through. The shield will, of course, block the regular photon, okay? But it will allow the hidden photon to go through because the hidden photon, that component of the hidden photon is completely sterile. It doesn't couple to anything. So that just goes through. But that's of no use to you because you want to detect that, right? So the only way you can detect that is by having the field oscillate back to a little bit into the regular photon. And that is something you can see, okay? So now we can ask what are the parametric suppressions in the story. So let's calculate the first part. So when I produce the regular interacting photon, it propagates out. It becomes a little bit of the non-interacting photon, the hidden photon. We can ask how big is that term, right? That basically goes as the electric field of the source. That's obvious, right? That's what's producing it. Times epsilon, also obvious, because that's the extent to which you can do this. But then it's proportional to essentially this sinusoid, which goes as mass squared L over omega, right? That's the oscillation piece, which should be familiar to you from neutrino oscillations, right? There's m squared L over omega, but L is the distance between the source and the shield. That's the extent to which you produced it. The detection works the same way, right? There is some hidden photon field that's coming in here, which is equal to this quantity there. And it's got to now oscillate back to excite your test charge there. And that will again have exactly the same parametric form, suppressed by an m squared there. Okay? And this is the concept behind a variety of experiments, such as these light shining through walls experiments. This is what they do, right? For example, they take a laser and they shine light. There's a wall that blocks the laser. And they try to see if there's a little bit of extra hidden photon going through, right? And if you could compute the answer as they did, you will find that the answer is proportional to mass to the fourth, coming from this m squared and that m squared. Right? That's basically what they do. And obviously that's a big parametric suppression when you're going to light masses. Right? It will seem pretty hopeless because you're fighting this big m to the fourth over there. Just a brief point here. And these laser cavity experiments are good. They search for micron wavelength photons, right? But again, we don't know what masses these things are. We should be trying to see as light as possible. Try to see whatever we can, right? Another very good way of searching for these are...
When you say repurpose, you could just set a limit based on what they have already observed.
Yes, you can.
Okay, you don't have to take new data.
Well, we'll talk about the longitudinal modes in a second, right? Because they do require a geometric change, it turns out. So those experiments exist, and they were actually built for that purpose, to find that. That's what they were trying to do. Instead of lasers, another perfectly reasonable thing to use are microwave cavities, right? We have a lot of experience in the accelerator community in building really good microwave cavities. One can have amazing resonances, like Qs of 10 to the 10, possible with superconducting resonators, and one can indeed have two cavities that are tuned to the same frequency. Then you look at the microwave sort of wavelengths, centimeter to meter scale. And the key idea will be the same thing. You have some source, that's some microwave cavity, that produces both the electromagnetic field and the hidden photon. You're just moving charges back and forth to do that here. And the normal photon will get blocked by the shield, right? While the hidden photons will go and try to excite the receiver cavity. And that's again a high Q cavity, so you can try to see it. So a variety of experiments have already been done with that concept. But once again, the signal scaling is the same, m to the fourth. At least that's what they believe. And my point is going to be that this is not the case. That one can actually do much better than what they claim. Instead of an m to the fourth, one can get an m squared effect, if you will. Okay.
So you have to change the distance between the two to scan different mass scales? The capital L.
Yeah. So what they typically do is that, they don't really do too much of a resonance scanning. They just build one experiment, and that's pretty much all they really are trying to do, right? So they have one mass they pick, and then they draw sensitivity curves like this. In fact, this is what the sensitivity curve is, right? They pick one value of the peak resonance, and then they say, well, here's how that value, because once you're at that frequency, you will produce hidden photons of frequencies well below it as well. Okay? So you can scan for all of them by just going at one point, essentially. However, because of that m to the fourth scaling, you have very little reach once you go below that peak.
Right.
Okay, that's it. So that's where the CROWS experiment, which is I think at CERN, as the name suggests, was able to do. Okay. And our point is going to be about the longitudinal mode, right? Why is the longitudinal mode different? The point is, the regular photon does not have a longitudinal mode, right? It is a massless particle, so the longitudinal mode is a gauge artifact. It doesn't exist. Okay. So now let's think about what the longitudinal mode is going to do for you here in this experiment. And there, the better basis to think about is the mass basis, right? So in the mass basis, let's say you move the charges back and forth. You've got 2 degrees of freedom. You've got the massless photon, which is coupled to with charge E, and there's a massive hidden photon that's got a small charge epsilon E, right? You shake this back and forth. When you produce the photon that's going out of there, the longitudinal mode, the massless photon does not even get produced. It doesn't exist, right? So there's no massless photon going through this. And then all you're therefore doing when you're shaking this thing is that you're producing the longitudinal mode of the hidden photon, right? But that guy is coupled with epsilon charge. When that guy goes and hits the shield, this is just a shield reacting to a tiny epsilon coupling, right? There isn't the regular hidden photon, the normal photon going with it. So that will just basically go through and excite your test charge. Okay? So the shield essentially permits the hidden photon to just go through without having to do any oscillation. Okay? Perhaps a more intuitive way of thinking about this is the following. Let's consider the transverse modes, right? In the case of the transverse modes, we said that the shield would block regular electromagnetism, right? How does that happen? I shake my fields over here. There's a propagating electromagnetic field, a regular electromagnetic field, that moves charges back and forth on that shield. And that shield therefore produces a cancelling electromagnetic wave, which when you go over here, will exactly cancel whatever was trying to go in initially. Right? So to cancel the effect completely was the fact that whatever incident wave you had here was cancelled exactly by the transverse mode produced, or the transverse mode of the regular photon produced by the motion of charges here. You cannot do that with the longitudinal mode, because your longitudinal mode will go in here, you'll try to excite charges there, but you can't produce a cancelling electromagnetic wave on this side because those longitudinal modes just don't exist. Okay? So in this case, you shake the skin, the longitudinal mode gets produced, it just goes through the shear directly. Okay? Yet you still have to pay the price for, I guess I'll just skip my slide ahead. So that's the key point here, is that you produce the longitudinal mode, it just directly goes through and excites the test charge. But of course, you still have to pay a price for the mass, right? Because if the mass vanishes, the whole effect should go away. And that, of course, is evident because if you look at the longitudinal mode, right, if I have a bunch of charges and I shake them back and forth, I ask what is the magnitude of the electric field of the longitudinal mode that I'm producing. And that is indeed proportional to m squared. When m squared goes to 0, the longitudinal mode is a complete gauge artifact, it goes away. Okay? So, therefore, what you see is that if you look at the longitudinal mode, the effect is proportional to mass squared. That's it. So we would argue that if you can detect the longitudinal mode, there's no reason why you cannot, right? It's just a regular, electromagnetic field that's propagating. Then the sensitivity will scale as m squared rather than m to the fourth. Okay, and in terms of whether or not this can actually be just used in normal experiments, the geometry is quite key to this. Okay, the point is that if you shake charges, the transverse modes and the longitudinal modes are going to be emitted in different directions. Right? So if you place your receiver cavity in the wrong place, then you'll be sensitive only to the transverse modes, and you'll have an m to the fourth scaling. While if you move it and keep it to the top, let us say, where the longitudinal modes are preferentially emitted, you're going to gain you'll gain the m squared sensitivity. Right? So the location of the receiver, in terms of where you're placing it, is very important in this case. Okay, that's the major point.
Which is the best? We really need orientation, right?
Yes, an orientation, exactly.
So what is the best orientation?
You want it to be on top, basically.
Now, what do you mean by on top?
In terms of good. So it's about like how you move your charges here, right? So for a cavity, this is a more complicated electromagnetic problem. But if you just have charges moving back and forth like this, right? The transverse modes go this way, but the longitudinal modes goes on the top.
Axially and angular.
Axially and yeah.
I see. So it's a question of where you want your detectors rather than
Yes.
rather than the cavity.
Correct.
Oh, okay.
Yeah.
See, orientation. That's what I
Yeah.
thought.
I'm sorry, I didn't quite get why you need the shield at all in this case. What is the shield doing?
Oh, because you're blocking regular electromagnetism,
Okay.
right? There's just stuff
Okay,
around.
okay.
Yeah, exactly.
So is there sorry, I think we may come to this, but in terms of the second cavity,
Right.
there must be a threshold for detection of
Yes.
anything.
Yes, exactly. So the basic assumption here is going to be that there is thermal noise in the cavity. That will be the limiting noise. Okay, and it seems like that is achievable. So essentially, if you look at normal electromagnetic field sensors like squids and things of that sort, the fundamental noise limits there are lower than the thermal noise. So the cavity itself. So we'll assume that the detector cavity is limited entirely by thermal noise.
So you put an array of squids or something.
Inside the exactly.
And there's no price for detecting those longitudinal,
There is an epsilon price in detecting it,
but not the m.
not the m squared. Exactly. Okay. So naively, if all we had to do was repurpose just the Crow's limit from what they published, right? If it turns out that their detector has some overlap with the longitudinal mode because these are kind of fairly big modes, centimeter scale, things like that. So they're not totally screwed, but it does dramatically change what they think their limit is versus what it actually is, right? Because of the m squared versus m to the fourth dependence on the light mass. Okay, that's the point. But Crow's was just an experiment that was not particularly even optimized to do this. We actually believe that, talking to our colleagues at SLAC, that one can actually get a pretty significant reach in this parameter space. I will show you the parameters in just a second. But you kind of see this, right? Which is really the difference between the previous scalings and our new scaling is obvious. Let's say you were able to do an experiment that could go all the way down there. If you thought it was m to the fourth, that's all you really get. Not a big parameter reach, but here you get a gigantic reach if you do it correctly.
So roughly speaking, on this plot here for the epsilon range
Yeah.
shown, what is the mass of the loop particle that will generate that kind of epsilon, and you'll assume some typical coupling, of course.
Typical. I don't know what you mean by typical coupling. I mean, I can take the gauge coupling really small, right? So then it's a question of what range you want to allow me to do that. So, you know, if it's a Stuckelberg kind of mechanism, then there is no really, there's no connection at all, right? There's just a hard mass that I put in the Lagrangian.
That's true,
Yeah. And then I just have like some free parameter that I can choose to be the gauge coupling. Okay. So what kind of thing would you need to get to something of this sort? You know, there are two things that we've talked to our colleagues at SLAC about, a stage 1 and a stage 2 experiment. Stage 2 is supposed to be more aggressive because, you know, it's colder. So the fundamental limit is that we're thinking that the receiver cavity is limited by thermal noise. So that tells you, you know, how much field can you really see. And for both experiments, the source is roughly like a 1 Tesla, you know, cavity, like something that you can hold 1 Tesla size magnetic fields. Cavity size is 10 centimeters and 1 meter, slightly more aggressive, larger cube and colder and longer integration time. That's roughly the, you know, ways in which this is more extreme than the other. But really, you can see our SLAC colleagues say that these numbers are not unreasonable, things that they actually think they can build. So really, there's I think a very interesting probe into this big parameter space that's possible, right? Getting all the way down to epsilons of 10 to the minus 14 nearly at this peak frequency of about 10 to the minus 6 eV.
I still don't understand where capital L is featuring in this, because that was in your the strength of the signal depends on L squared, right?
That was the case for the transverse mode, because there's an oscillation.
Okay, right. Not in the,
Right.
There's no oscillation.
Oscillation here, yeah. Here, the size typically has to do with things like, well, if I'm going to a certain low frequency, right, I need my cavity to be big enough to resonate, right? So it's really the wavelength that picks it up.
And there's some sort of flux coupling also, right? I mean,
that's right. So if I have a squid or something and I'm trying to detect it on that side, then the larger the size of my of electromagnetic region, second thing,
okay.
then the larger the pickup will be. Okay. Exactly. All right. So I'm going to move on to the next part of the talk, which some of you may have already heard before, which is how do you detect this thing if this happens with the dark matter, right? And the concept is very simple. If this hidden photon happens with the dark matter of the universe, everywhere in the universe there's going to be a time-varying electric field associated with it. Much like how the CMB, right, is a time-varying electromagnetic field everywhere. So you can stick a little detector of electromagnetic field and you see the CMB. So similarly, if this very light particle happened to be the dark matter, there's going to be a time-varying electric field, the hidden electric field, oscillating everywhere in space. And what you do is if you just put a normal detector of electromagnetism, you'll get all the crap that we have typically. So you put a Faraday shield, and then you go inside the shield and sit there with some detector. The dark matter will get through and excite it. Right? That's the basic idea.
So you're going to be focusing in on the longitudinal?
That's right. So the there yes. I mean, like it sort of turns out that pretty much any production mechanism that you think of for these things will produce a longitudinal mode, and there's not a big difference there.
but if it's like a relic, it's isotropic and unpolarized.
It is isotropic and unpolarized over long length scales. Okay, but over short length scales, it doesn't have to be. Okay, right. So exactly. So in fact, that's one of the points here. So let me just go through that slide. Just a very brief motivation there. Turns out that bosons whose masses are larger than about 10 to the minus 20 eV, things of that sort, can be really good dark matter. Axions are the canonical example, but there's no reason to just stop with axions. Many other things possible. They obviously have to have very high occupation number because if they have to reproduce the observed dark matter density with such a light number, with such a light mass, it better be the case that the number density is huge. And the hidden photon is a perfectly good example of something that could be the case. If this thing is a dark matter, then the entire universe is just filled with a dark E prime field that's oscillating back and forth. Exactly like how the CMB is it's a regular electromagnetic field that's oscillating back and forth. Here, just the E prime field that oscillates. Because it's non-relativistic, the magnetic component is smaller by a velocity, okay, of about 10 to the minus 3. So E prime is a dominant thing. And then how big is that E prime? You can just equate that to the local dark matter density. That gives you a good estimate of how big that amplitude is going to be. Indeed, this will be a random direction. This is going to be Lorentz braking. Okay, you have a vector in space that's oscillating back and forth. But the couplings are really small, right? So the CMB breaks Lorentz invariance in a sense, and doesn't break, rotational symmetry, of course, but it does create a frame for you. Similarly, this thing also creates a frame for you, but it's sort of very small coupling to us, so we don't really have any good bounds yet on that kind of thing. This field is oscillating back and forth at a frequency equal to the mass of the particle. That's exactly what it's doing. And the field will also be coherent for a time that is order about 10 to the 6 oscillations of this period. Okay, that basically means if you have a detector and you're trying to build some kind of resonator, right? You can have a Q of about 10 to the 6 before the field becomes random again. Okay, I can explain that to you offline if you want more information. But that's basically coming from the fact that the field has a kinetic energy in a galaxy, which spreads out its power from everything being the same frequency to the inverse of the kinetic energy.
So 10 to the minus 3 is just to make it cold?
Well, that's something that we know from the galaxy, right? So galaxy, we know that the velocities of dark matter is 10 to the minus 3.
Okay, is that independent of what type of dark? Okay.
No matter what dark matter is, if it's dark matter, right, then gravity will act on it identically. It doesn't care.
I see. Okay.
So exactly. So
Okay.
no matter what you do, is always that answer.
Okay.
Okay. I won't go to the cosmology here. There are interesting things that you could talk about if bicep had been true, but that doesn't seem to be the case. So we'll ignore that for now. Okay. So the concept again is, so actually some of these numbers are very interesting. Let's say you plug in the value of the E prime field and, you plug in the value of the local dark matter density to figure out how big that dark electric field is. It's a pretty big field, it's like 2000 volts per meter. It's huge, right? Of course, the coupling is very small, so that's why we're not getting fried by it, right? But it's a pretty damn big field, right? And it's oscillating at this frequency with this thing. And indeed, the idea is that it's just that it will obviously excite electromagnetic resonators. That's what electromagnetic resonators do. You pump them with the time-varying field, they get excited. So any electromagnetic cavity experiment, such as ADMX, right? ADMX has been trying to search for axions for a long time. They are a resonant electromagnetic cavity, so they're automatically sensitive to these things. But those experiments are, operate over a very narrow range of frequencies, 10 to the minus 4 to about 10 to the minus 6 eV, right? Those are the size of cavities that can actually physically construct, which is where these things operate. And that's pretty much all they're really sensitive to right now.
Part of your parameter space, epsilon versus mass, is excluded by the requirement the lifetime.
Well, the lifetime of this thing is, enormous, right? Because it's not like it can even decay to anything. Pardon me?
Depends on epsilon.
Exactly, and the
So
mass.
that's why I'm saying, and the mass.
Right, that's
there's
right.
a certain region that is excluded by this constraint.
Exactly, but like those constraints are not all that severe. So on anything that I'm showing here, this thing is basically stable. Well, it can't even decay into anything, right? It could probably go into photons or something like that.
Photons.
At some, but that rate is just super small. Yeah.
So to understand that, should it be like volt prime because the induced voltage will be epsilon?
Epsilon, that's correct.
Okay.
But sure.
Okay.
Yeah, that's right. Right. There's really an epsilon sitting there.
The
which
meaning
why
of
we
that
haven't
volt
seen it.
is something else, right?
Precisely.
Okay.
Absolutely. Yeah. So we propose in this paper here that instead of just sticking with electromagnetic cavities and being restricted with the range of frequencies that are operated, one could construct LC oscillators, radio sets, right? Those things can indeed resonate over a much wider range of frequencies. We know how to do that technology really well, and that will allow us to probe much lower masses. That's the idea. So here's the experimental setup. If this thing is a dark matter, there's a time-varying E prime field everywhere. We take a metallic box, a Faraday cage, blocks regular electromagnetism, right? The dark photon should still go through, and you should be able to excite something in there. But there's an important point here, which is that as the dark photon moves through, right, the E prime field on this conducting shield, it will also generate currents on that shield. Because, that's what it's going to do. Currents, electromagnetic particles are coupled to it. And those conduction electrons will actually create regular electric and magnetic fields inside the shield. Right? Because you're moving charges on the shield, you're going to create regular electromagnetic photons. So it turns out that the net effect of this whole story is that this dark E prime field gets converted to a regular magnetic field, the normal magnetic field of electromagnetism, which is of this magnitude. It's proportional to epsilon, which it has to be because that's the rate at which you're moving anything, times 10 to the minus 5 Tesla, which actually is the same number as 3000 volts per meter. Okay.
So you said locally it's different because if it's isotropic, the net current is zero. So somehow it has to be anisotropic.
Yeah, exactly. So the thing is, these masses are so small, right? That if you look at like a little box of size 1 meter or something, in that 1 meter there's a fixed direction, right? Because the actual coherence length is 1 over the mass, and that's an enormous length scale. It's enormous compared to humans, but small compared to galaxies.
Okay.
Right? That's
So let's see, once again, the epsilon comes just from how much E prime connects to the electrons.
Electrons.
In the,
in the shield, right?
shield.
Exactly, and exactly. So that creates a tiny current there, and that tiny current will source a magnetic field over there. Okay, so that's the basic answer. Okay, and there is an important effect, which is the mass times r, because once again, this effect also better go away when the mass goes to 0, right? And that's, I mean, I can go through that in more detail if you want offline. It's not terribly interesting. It's just sort of seeing that another way. That's basically what happens. And so what we're going to do is, inside that shield, you just stick an LC oscillator, right? And now that you have a regular magnetic field inside the shield, that will couple with the inductor and have it excited. And that is something you can then see. Once again, in this story, what will limit us, ultimately, in terms of our sensitivity, is the thermal noise on the LC oscillator. Okay? That's what will prevent us from going to arbitrarily low levels. So this is a proposal that we're working on right now with Kent Urban at Stanford. And, here are some couple of parameters. Stage 1 and stage 2, more aggressive numbers, 4 Kelvin, 10 millikelvin, things of that sort, like bigger size, better coupling to the squids, etc. And one can actually see that, these experiments really have the ability to probe pretty deep in this parameter space. Like stage 2 here, for example, can get all the way down to epsilon nearly 10 to the minus 17, if you will, okay, at this very low mass range of about 10 to the minus 7 eV. So I think there's a very exciting program here of, anything that range is possible. I think there's a very interesting set of experiments that can be done. These are relatively low-cost setups, but has a very big payoff that you can try to find these very interesting kinds of problems.
So I'm just curious, the box that you draw, the Faraday cage in this case,
Yeah.
this is no longer a superconducting cavity, right? So there has to be some leakage.
It can be a superconducting cavity. There's no reason why it can't be a superconducting cavity, right?
Okay, so,
Yeah.
but even with...
And the thing is, it's a question of...
zero even for superconducting, is it perfectly zero?
Well, for AC currents, so here's the bottom line, right? AC currents AC fields are easier to shield than DC. Because if you're doing DC, there will be some flux that gets stuck somewhere, and then bad things can happen, right?
So there's like some Meissner depth or whatever.
That's right. The Meissner depth is microns, right? So you just have a...
Even at, what is frequency dependent?
Yeah, but it's not a particularly, we're talking about gigahertz, things like that, right? Things that we, it's true that if you go to optical, things of that sort, then, above that, the Meissner depth gets very long, right? But for these frequencies, it's fine. Okay.
So, but if you factor that into your model, or you assume zero background, zero leakage of EM?
We have assumed zero leakage of EM, and, our examiners think that's a reasonable assumption. That we still think thermal noise will be the ultimate killer rather than things of that sort. Okay. And the key thing is, this is a case where you can really test if what you're seeing is really a physical effect like dark matter, as opposed to it being some leakage, right? Because what you really want to do is you want to build 2 such experiments, right? These are pretty small scale experiments, and the dark matter has a very long coherence length, kilometers or thousands of kilometers, depending on its mass. So really what you would do is you would build one experiment in one location and then go some long distance away in another location, and then you cross-correlate the signal. You see the same signal shows up in both places, matched in frequency and phase for a long time. Okay? If you saw that, you would be very convinced that what you're seeing is dark matter and not some random leakage because you screwed up on your shield. So I think if you can build it and you detect it, you really would know that what you're seeing is something fundamental. Exactly. So that's basically all I wanted to talk about. So thank you very much for having me over. Yes.
Return to the stability issue. There are massless neutrinos that
Yes.
decay at 3 level to the neutrino.
This thing does not couple to the neutrino because the neutrino has 0 electric charge.
But the Z couples to neutrino.
Right.
And the U1 that mixes with your extra U1
Yes,
is
exactly.
part of Z, so it would decay to neutrinos as well.
Precisely. It will be suppressed, however, with a weak scale, because it doesn't go to the Z, right? It's a high dimension operator, and you're talking about a...
No, it's not high dimensional.
No, like
it's a kinetic mix.
But if the Z was arbitrarily high, it'll decouple, right? So your whatever is causing this decay will be suppressed by powers of the Z mass, all right? And if you think about it, we're looking at an MEV splitting, which is what you have for neutrons, gives rise to a decay that is over 1,000 seconds, and this is 10 to the minus 6 something eV raised to the 5th power. Doesn't happen.
It'll have to be W loop, right? The decay will-
All of those are high dimension operators that are
There's no direct
suppressed.
decoupling. So
No, look, it's all suppressed with a weak scale. Right, that's it.
yeah, it's suppressed, that's right.
And it's a suppressed rate, and you can calculate how suppressed it is. It's very long.
And there's no bounds from nuclear synthesis.
These are super cold.
That's a contribution to the energy density that changes the expansion rate.
Yeah, this is just, this is basically dark matter, right? So, is equal to dark matter density, doesn't do anything. So the key point, thanks for bringing it up, is the fact that these couplings are so small that these guys are never thermalized in the history of the universe. Right? So it's not like there are a hot population of photons going around there. I should have mentioned that. Okay. Pardon me? Yeah.
Feebly interacting.
Feebly interacting, yes.
The key is that for any human scale, these things are non-isotropic.
Yes.
It's just very large coherence length.
Very large coherence length, exactly. Yeah, so it's a very interesting scale, right? It's isotropic on galactic scales, but for humans, it's something we can do. And certainly the frequencies are also incredibly interesting. Like, these are frequencies where we have built a lot of electromagnetic instrumentation to go after it. Right, so it's not like some super high energy thing, or if it happened to be, say, really, really low frequencies, 10 to the minus 30 eV, then you would never see the oscillation because we don't live long enough. Right? So these oscillations all happen at frequencies that are very human. I mean, things that you can build something and really go and really go
If
for
I
it.
take the whole Earth,
Yeah.
just there's an overall induction
Yes.
happening, right?
Yes, yes.
The wavelength is larger than the Earth.
Exactly.
Right?
Yes.
So people are trying to calculate stuff like this, right? So there's the Earth and the ionosphere form a cavity as well.
Sure.
So what would be the resonant frequency that we should see
I think it's
induced
just
due to that? Then I don't need to do all this because there is some coherent frequency already present, just natural effects.
Yeah, it's just a question of the fact that the Qs are not going to be very big because the other dissipative modes, and we don't have any it's not a precision measurement thing, right? This is just some atmospheric thing. We don't have precision detectors figuring out exactly what's happening. So we saw it really, really big amounts. Okay. Yeah.
Interesting. So Jack had a question.
Yeah.
I just wanted to come back to the dark matter. I'm trying to get the. So you have to have enough of these, despite their low mass, to have a real gravitational effect.
Yeah, indeed, yes.
So how are you getting so many of these things?
It is just an initial condition, okay? So if these fields existed, right, then in the very early universe, the field would have a non-zero initial value, okay? If the field had a non-zero initial value, there would be energy density in it.
Right, but if you imagine a big bang, suppose it was a big bang of normal matter.
Yeah.
Is there any way you can produce this many?
It won't be produced from the standard model. So they're produced from the fact that, let's say inflation, right, standard initial story. At the end of inflation, various fields have to have various initial values. It's reasonable that they would have some initial value.
Well, that's what I'm questioning, isn't it?
It may be 0%.
Well,
I think zero is an artificial choice,
I'm
right?
trying to understand why, the usual symmetric way of thinking about how things might happen in the early universe.
Right.
You would get a lot of these guys. Now, of course, if you had a charged particle that was produced in the early universe that was making these things, then maybe you could...
That's not what we're talking about, no.
I'm sorry?
That's not what I'm saying, yes.
Right, yeah, that's not what you're saying.
No.
So nobody's done that calculation to see...
Well, this is in a sense not calculable, right? Because in the inflationary story, here's what will happen. There is some field, this dark field, right? That field, in general, will have an order 1 initial value. So in fact, most of the time, what you end up getting is the fact that these fields can produce way too much dark matter. Because if you look at it, they could have some gigantic field value in the early universe. And they have a tiny mass, so they don't do anything. Yes?
Does that require super Planckian field exclusion?
Not necessarily. So that's a question about really where the mass happens to be. So roughly around 10 to the minus 21 eV, turns out, is where you get Planckian excursions. So anything below that is sub-Planckian excursions. So in fact, that is one of the kind of acute fact is that if you look at exactly where the current bound in the dark matter is, about 10 to the minus 21 eV, okay? The dark matter can't be lighter than that because it won't fit into the galaxy. It has a de Broglie limit that is much bigger. So at 10 to the minus 21 eV, you can calculate how big should the field excursion have been in the early universe for it to be dark matter today. And that field excursion is order M Planck.
For what inflation scale it matters what
The inflation scale does not matter, right? Because the field remains stuck until Hubble becomes order of the mass of the field. So it's entirely a low energy calculable.
And this is especially undefinable, I guess, in the Stuckelberg approach, because you don't have these guys coupling to anybody. It's just that the Big Bang somehow creates this initial field condition.
Sure. Field value, that's it, yeah.
I don't know, is that reasonable?
I don't know what the Big Bang is, so it's hard for me to speculate on what is reasonable and unreasonable about the Big Bang.
And it's got to have some value.
Yeah.
Zero is completely artificial because the
Yeah.
potential is just flat, 10 to the minus whatever EV.
Right.
And with super high temperature, why should it pick the minimum? There's no anything about that.
Well, I'm not saying that,
I mean, that's the standard axion cosmology.
yeah. So the idea of some string modulus or something couples to these things, and that's the axiom game, isn't it?
And the axiom game is, once again, there's an initial condition, right? It's something we don't know what it is. And instead of legislating what it is, if you find it, you actually know what happened. So that's really how I would look at it.
So if you want to produce like standard reheating after inflation?
No, the couplings are super small, right? So the standard model doesn't produce it. Now, of course, you could have something else that couples to it and produces it strongly. Look, we don't know anything about what reheating really is, right? So you have complete freedom there to produce whatever you want.
Yeah.
So all we can say is that given its couplings to the standard model, you can't produce it, but reheating could. I mean, that's another story.
It could couple to inflated, right?
Sure. But, we don't know that either, right? We don't know what exactly. So that's it.
More questions? So let's thank Surjeet again.
Thank you.
So Max, is it tomorrow?
Yeah.
Okay.